Most important equation in quantum mechanics so far, Bohr's equation. And this equation is going to tell us about the energy levels of the hydrogen atom. That's right. It's going to tell us that energy levels are discretized. Now, we already knew that before when solving the one-dimensional Schrodinger equation, but now we're going to know something very specific that we knew a long time ago, but we didn't know the reason for. These energy levels somehow decrease with an inverse quadratic rate. How is that possible? Well, the secret all lies in Coulomb's law, which tells us that the potential of the hydrogen, of the electron in a hydrogen atom, is E squared over 4 pi epsilon naught r, and Schrodinger's equation, the radial component. Recall that we've already solved Schrodinger's equation for the time component, the angular component, and the other angular component, down to a few constants. But something we haven't got a general form for is the radial component, because that depends on the potential function. But now we have a specific potential function, so it should be fairly simple to solve. Schrodinger's equation for the radial component, minus h bar squared over 2m, no, it's not ready yet. It kind of looks like it's ready, but it's not. U double prime plus the potential function minus, actually, why are we using U? Let's use psi r. Plus h bar squared over 2m. This is the centripetal term, which is what makes this so difficult to solve, because it's the only addition from the regular Schrodinger equation, which we've already solved for a lot of different potentials. The separation constant over r squared is equal to ER. And I'm pretty sure there's an R on the outside of this. Just to be sure. Yep. Okay. No, this is a psi r, and this is also a psi r. Okay, so how do we even attack this? Well, there's not a good way to solve this directly. How does this look? Let's divide both sides by e. We get minus h bar squared over 2me psi r double prime plus u over e psi r plus h bar squared over 2m l times l plus 1 over r squared. There's an e over here, psi r, and then you're going to have the minus psi r is equal to 0. So now I'm going to take, let's call it c is going to be, yeah, I know, very original name, the square root of minus 2me over h bar. So that makes this c squared, and that allows us to abbreviate this and that. So you get u over e psi r. In fact, let's factor out psi r, plus h bar squared over 2me, which actually here becomes minus c squared l times l plus 1 over r squared psi r plus 1. And what is u? Well, it's u squared 4 pi epsilon naught e. This is pretty much ignorable. It's just a constant times r. So at the end of the day, I'm just going to abbreviate this as, no, let's abbreviate this as C2 because it's easier. And you get C squared plus C2 over R minus C squared L times L plus 1 over R squared plus, was that always a plus 1? That wasn't, was it? minus 1 has to be equal to 0. So first things first, let's look at what happens when, no, there's a psi r at the end here. This keeps getting more complicated. First things first, let's see what happens when r approaches infinity. Well, that's going to disappear, this is going to disappear, and so all that's going to happen is you're left with c squared psi r double prime minus psi r is equal to 0. Hold up a minute. This is a very regular separable. No, it's not separable. We just use the ansatz. Where's my marker? We take psi r is equal to a e to the r. No, I can't use r.
Like blackboard, can you erase blackboard and do it?
Okay, what's a good number that we can come up with? Good constant name. Let's call it. Oh, I'm dropping everything today. Let's call it A. So, if we plug in the ansatz, psi r is equal to A E. No, I already used A. Let's use B. Going from A to B. So, we get c squared psi r double prime is equal to psi r. So, of course, that's going to become c squared ab squared. We don't need the a. Is equal to 1, which means that b squared is just equal to 1 over c squared. And so b is equal to 1 over c. So you get e is 1 over ct. Nice. So now, what else can we do? This is how things are going to look when we're very close to infinity. Now, when you actually think about it, since we took the square root, this is going to be a1 e plus 1 over ct plus a2 e to the minus 1 over ct. But,
you have all the board over there. Why you are on the
I have some purposes to use it for. But, think about it for a second. As r approaches infinity, this is going to blow up, but this is not going to blow up. So that means that we're going to replace this with only the term that doesn't blow up, because we want the wave function to actually mean something. We want it to be normalizable. And so we make the statement that near or as r approaches infinity, psi r is approximately e to the minus 1 over c r. Nice.
Yeah, don't use it.
So now, what about close to the origin in the other direction? Well, that means that this is going to be the biggest term of them all, because it's in inverse quadratic. It's going to outgrow just 1 over r, and it's definitely going to outgrow minus 1. Which means this simplifies to c squared psi r double prime plus, well, we eliminate everything except this guy, minus c squared L times L plus 1 over r squared times psi r is equal to 0. So, rearranging, this is equal to c squared L times L plus 1 over r squared psi r. And so, this solution definitely doesn't depend on the value of c. So, what do we get? This can be assumed to be some power rule, because, well, what we're seeing here is that the degree of the function goes down by 2 when you take the double derivative, which means that it has to be a power rule, right? So we assume it's some monomial. Let's call it br to the k. And so we get br to the k minus 2 times k minus 1. Oh, and that's why L times L plus 1 is so useful here. It's also very useful for the way the power rule works, is going to be equal to L times L plus 1 B R to the K minus 2. So the B to the R K minus 2 cancels out, and we get that K is just equal to L plus 1. Nice. So since K is equal to L plus 1, the general solution looks something like this. Nice. So now we know that, and I'm going to use orange, as R approaches 0, psi R is approximately BR to the L plus 1. Now, this is all well and good, but how do we proceed from here? You know the function's general behavior, but we still have no idea what's in the middle. So what we have so far is, I'm going to use the whiteboard for 1 second before switching back to the blackboard. We know what the beginning looks like. It's going to be BR to the L plus 1. So it's going to... So we know what the beginning looks like, and we know what it's going to approach. So we know this part, and we know this part. But what the heck is in between? That is what we're going to dedicate the rest of today to figuring out. So we can't really progress from here. So all we can do is hope and pray that if we strip the function of these two asymptotic behaviors, hopefully we'll get a mildly similar function that is generic at the beginning, will tell us the middle behavior, and is generic at the end. But how do we go about this? Well, we're just going to set psi r over line is equal to psi r multiplied by the inverse of this, which is going to be, I don't care about the b, just let it be b, and this should have the amplitude here. I don't care about that either, it can get absorbed into this. In fact, let's just call it a, psi r times 1 over r L plus 1, or r to the minus L minus 1, and you have e to the 1 over cr. That's essentially how we remove both of the tail ends. So that means that towards the beginning and towards the end, this should convert to 1, or a, whatever it is. But what will it look like in the middle? Well, that's something that we're going to be saving for next episode. Thanks everyone for watching. We'll be analyzing the middle behavior by taking the double derivative of this, then plugging it into that equation.